Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The axiomatic assent, a critical evaluation of Ernst Zermelo's 1904 proof that every set can be well ordered. Ernst Zermelo's 1904 paper, proof that every set can be well ordered, stands as a landmark and perhaps a lightning rod in the history of set theory. This essay undertakes a rigorous examination of the internal logic and foundational claims presented within that paper. It will proceed by meticulously dissecting the structure of Zermelo's argument, scrutinizing the claims made in each successive section, and assessing the validity of the reasoning employed. It seeks to offer a detailed and nuanced understanding of the genesis and impact of this monumental proof, one that forever altered the mathematical landscape. Section 1 Introduction and the Well-Ordering Principle. The introductory section of Zermelo's paper establishes the central problem, demonstrating that every set can indeed be well-ordered. He positions his endeavour as a response to earlier efforts, particularly those of Georg Cantor, who, while convinced of the truth of this proposition, lacked a rigorous, universally accepted proof. Zermelo emphasizes the foundational importance of this principle for establishing a clear and unambiguous hierarchy among infinite sets, specifically concerning their cardinalities. He outlines his intention to provide a purely logical proof, independent of any intuitive notions about the nature of sets or infinity. A key element introduced earlier is the concept of definite sets. He describes this as sets whose definition leaves no ambiguity for the inclusion or exclusion of a given member. Contemporary interpretations have connected this idea to the concept of a set's characteristic function. This introduction is critical, as the ambiguity surrounding the definiteness criterion would later become a focal point for critiques of his proof. The introduction is itself a claim. It claims the existence of an ambiguity. This claim sets the stage for the explicit logic of mathematical proof. Section 2 The Axiom of Choice and Elementary Assumptions. This section explicitly introduces the axiom of choice, which forms the bedrock of Zermelo's entire argument. He states it in a form close to the modern understanding. Given any collection of non-empty, pairwise disjoint sets, it is possible to select one element from each set. What is of significant interest is that Zermelo presents the axiom not as a self-evident truth but as an assumption necessary to overcome perceived limitations in existing logical frameworks. He acknowledges the potential for controversy surrounding this axiom but insists on its indispensability for achieving his objective. He also lays out several other elementary assumptions, such as the standard properties of sets, subsets, and the notion of an elementary chain, defined as a sequence of sets each containing the previous one. His formulation of the axiom of choice is in itself an assertion. It presents a selection function as existing for any set of non-empty disjoint sets. This is the core claim driving his deduction process. Section 3 Definition of a gamma set and its properties. Zermelo introduces the concept of a gamma set, a specific type of well-ordered subset of a given set M. A gamma set possesses the property that, for any element x within it, the section of the gamma set consisting of all elements preceding x is equal to the intersection of M with some member of a predefined set K of subsets of M. The set K is related to his axiom of choice. Zermelo asserts that gamma sets can only be extended in a specific, well-defined manner. This section relies heavily on the assumed existence of a choice function, which dictates how elements are selected from the relevant subsets. He argues that if two gamma sets are distinct, then one must be a section of the other. This section establishes crucial properties of these gamma sets, which are essential for the subsequent proof. He explicitly claims that the gamma sets are totally comparable by the section-off relation. This is a powerful consequence, driven by his previous assumptions and choice mechanism. He directly leverages this claim for further proof steps. Section 4 Prove that the union of all gamma sets equals the original set. Here, Zermelo presents the core argument of his paper. He aims to demonstrate that the union of all possible gamma sets constructed from the original set M is equal to M itself. He proceeds by contradiction. Supposing that there exists an element within M which is not contained in any gamma set, he then attempts to construct a new gamma set by extending an existing one with this missing element, demonstrating that the existence of such an element leads to a contradiction. This construction relies heavily on the properties of gamma sets established in the previous section, and on the application of the axiom of choice to select the missing element. In essence, the argument shows that if M is not the union of all gamma sets, then we can always construct a gamma set that contradicts this assumption. The proof's success relies on the well-defined nature of the extension mechanism and the completeness of the collection of gamma sets. Zermelo's claim that this assumption implies a contradiction within the boundaries of set theory axioms, therefore validating his initial claim. The union of all gamma sets must equal the original. Section 5 well-ordering of the gamma sets implies well-ordering of the original set. This section completes the argument by showing that if the union of all gamma sets is equal to M, and the collection of gamma sets can be well-ordered, then M itself can be well-ordered. He defines a well-ordering on M by inheriting the well-ordering of the gamma sets. Specifically, he asserts that two elements in M can be compared based on the gamma sets to which they first belong. If one element appears in a gamma set earlier in the well-ordering of gamma sets than another element, then it is considered less than the other element in the well-ordering of M. He concludes that since a collection of gamma sets can be well-ordered, and their union equals M, then M itself can be well-ordered. This section bridges the gap between the abstract construction of gamma sets and the desired conclusion. The core claim is that the inherited order relation will constitute a valid well-ordering for the original set. Section 6 critique regarding the definition of definite. One of the initial criticisms levelled against Zermelo's proof centred on his usage of the term definite set. As understood within the context of 1904, the criterion for what constituted such a set lacked complete clarity. Critics like Poincaré argued that the reliance on a definite property could introduce circularity into the argument, as the very notion of definiteness might implicitly rely on the ability to well-order sets. If Zermelo's definition of definite presupposed a well-defined means for distinguishing elements, the proof could be seen as assuming the conclusion it aimed to establish. The claim here is that Zermelo's initial formulation failed to provide a sufficiently precise definition of this crucial term, leaving the door open for subjective interpretations and potentially undermining the rigor of the entire argument. Later formalizations of set theory, particularly those based on the Zermelo-Freenkel axioms, addressed this concern by eliminating the need for such an ambiguous Section 7 scrutiny of the axiom of choice and its acceptance. The axiom of choice, the linchpin of Zermelo's proof, faced significant opposition. Many mathematicians, accustomed to constructive methods, found the axiom to be non-intuitive and potentially paradoxical. They were uncomfortable with the idea of selecting elements from infinitely many sets without a clear rule or algorithm for doing so. However, prominent mathematicians such as Hilbert championed the axiom of choice, recognizing its power and utility in solving problems across various branches of mathematics. Over time, their axiom of choice gained increasing acceptance, due in part to its successful applications and its role in simplifying proofs of many important theorems. However, debates about its legitimacy and implications continue to this day within the philosophy of mathematics. The issue is not strictly about the truth of the axiom, but its implications for mathematical intuition and proof techniques. The claim is that a simple assertion of an independent axiom enabled the entire argument. Section 8 revisions and refinements of the proof. Zermelo's original proof underwent several revisions and refinements in response to criticisms and suggestions from other mathematicians. In 1908, he published a revised version of his proof, aiming to address some of the concerns regarding the definition of definiteness and the reliance on the axiom of choice. This revised version placed greater emphasis on the operational aspects of the proof, demonstrating how the axiom of choice could be used to construct a well-ordering relation explicitly. He also clarified the role of ordinal numbers in the argument, providing a more rigorous framework for understanding the structure of well-ordered sets. These revisions helped to solidify the proof's validity and increase its acceptance within the mathematical community. The claim is that he significantly strengthened his original argument by addressing specific shortcomings. Section 9. The independence of the axiom of choice and its implications. A profound development in the history of set theory came with the discovery that the axiom of choice is independent of the other axioms of Zermelo-Freenkel set theory ZF. This independence was demonstrated by Gödel, who showed that if ZF is consistent, then ZF together with the axiom of choice is also consistent. Subsequently, Gouin proved that if ZF is consistent, then ZF together with the negation of the axiom of choice is also consistent. This means that the axiom of choice cannot be proven or disproven from the other axioms of ZF. This independence result has far-reaching implications for the foundations of mathematics. It suggests that the axiom of choice is not simply a matter of logical necessity, but represents a fundamental choice about the nature of sets and mathematical reasoning. This claim significantly altered the landscape of set theory. Section 10. The impact of Zermelo's proof on set theory and mathematics. Zermelo's proof of the well-ordering theorem had a transformative impact on set theory and on mathematics more broadly. It legitimized the use of the axiom of choice, opening the door for its widespread application in various areas of mathematics, including analysis, topology, and algebra. The well-ordering theorem itself became a fundamental result in set theory, with numerous applications in proving other important theorems. The proof also stimulated further research into the foundations of mathematics, leading to the development of new axiomatic systems and a deeper understanding of the nature of sets and infinity. It fueled the development of various concepts. Section 11. Alternative formulations and equivalents of the axiom of choice. Over time, several alternative formulations of the axiom of choice have emerged, each expressing the same underlying principle in a different way. One well-known equivalent is Zorn's lemma, which states that if every chain in a partially ordered set has an upper bound, then the set contains a maximal element. Another equivalent is the Hausdorff maximal principle, which states that every partially ordered set contains a maximal chain. These equivalent formulations have proven to be useful in different contexts, providing alternative ways to apply the axiom of choice in solving mathematical problems. The existence of these different forms highlights the fundamental nature of the axiom of choice and its pervasive influence on mathematical reasoning. The claim is that, while different syntactically, these lemmas exhibit identical logical consequences. Section 12. The role of ordinal numbers in well-ordering. Zermelo's proof relies heavily on the concept of ordinal numbers, which provide a way to enumerate and compare well-ordered sets. Ordinal numbers extend the natural numbers to include infinite numbers, allowing for a hierarchical organization of infinite sets based on their order type. In Zermelo's proof, ordinal numbers are used to index the elements of the gamma sets, providing a precise way to define the well-ordering relation. The properties of ordinal numbers, such as transfinite induction and transfinite recursion, are essential for proving the well-ordering theorem. Ordinal numbers provide a way to rigorously capture notions of succession and precedence, essential for defining well-orderings. Section 13. Constructive alternatives to the axiom of choice. The axiom of choice has faced persistent criticism from mathematicians who advocate for constructive methods, which emphasize the need for explicit constructions in mathematical proofs. Constructive mathematicians reject the axiom of choice because it allows for the existence of objects without providing a means for actually constructing them. Alternative approaches, such as intuitionistic set theory, seek to develop mathematics without relying on the axiom of choice, focusing instead on constructive principles. While these constructive approaches have not gained widespread acceptance, they offer valuable insights into the foundations of mathematics and challenge the assumptions underlying classical set theory. The core claim is that the axiom permits non-constructive results. Section 14. The implications of the well-ordering theorem for cardinality. The well-ordering theorem has profound implications for understanding the cardinality of infinite sets. It implies that every set can be assigned a cardinality, which measures its size. Since every set can be well-ordered, it can be put into a one-to-one correspondence with an ordinal number. This allows for a comparison of the sizes of different sets. Even if they are infinite, the well-ordering theorem also establishes that the cardinal numbers are well-ordered, meaning that any collection of cardinal numbers has a least element. This has significant consequences for the study of infinite sets and their properties. The claim is that his proof directly enabled a method to measure infinity. Section 15. The continuum hypothesis and its relation to the axiom of choice. The continuum hypothesis is a famous conjecture in set theory that states that there is no set whose cardinality is strictly between that of the natural numbers and that of the real numbers. The axiom of choice plays a crucial role in the study of the continuum hypothesis. Gödel showed that if ZF is consistent, then ZF together with the axiom of choice and the continuum hypothesis is also consistent. Cohen later proved that if ZF is consistent, then ZF together with the axiom of choice and the negation of the continuum hypothesis is also consistent. This means that the continuum hypothesis is independent of ZF and the axiom of choice. This independence result highlights the limitations of axiomatic set theory in resolving certain fundamental questions about the nature of infinity. The claim is that the CH is independent of both ZF and axiom of choice. Section 16. Applications of the well-ordering theorem in analysis. The well-ordering theorem, although seemingly abstract, has applications in various branches of analysis. For example, it can be used to prove the existence of non-measurable sets, which are sets of real numbers that cannot be assigned a measure in a consistent way. The well-ordering theorem is also used in the proof of the Hahn-Banach theorem, a fundamental result in functional analysis. These applications demonstrate the power and utility of the well-ordering theorem in solving problems in analysis, even though it is based on the non-constructive axiom of choice. Zermelo provided a means of demonstrating the existence of highly pathological sets. Section 17. Connections to the Banach-Tarski paradox. The Banach-Tarski paradox is a startling result in geometry that states that a solid sphere can be decomposed into a finite number of pieces, which can then be rearranged to form two solid spheres, each identical to the original. The proof of the Banach-Tarski paradox relies heavily on the axiom of choice. The paradox highlights the counterintuitive consequences of the axiom of choice, particularly in the context of geometry and measure theory. It demonstrates that the axiom of choice can lead to results that seem to defy our everyday intuitions about space and volume. The paradox exposes the counterintuitive results that depend on the axiom. Section 18. Philosophical implications regarding existence and constructibility. Zermelo's proof of the well-ordering theorem raises profound philosophical questions about the nature of mathematical existence and constructibility. The axiom of choice asserts the existence of certain object choice functions without providing a means for constructing them. This raises the question of what it means for a mathematical object to exist if it cannot be explicitly constructed. Constructivist philosophers argue that mathematical objects only exist if they can be constructed in some way, while Platonist philosophers believe that mathematical objects exist independently of our ability to construct them. These philosophical debates continue to shape our understanding of the foundations of mathematics. The claim is that the paper directly forced a debate over abstract mathematical realism and constructivism. Section 19. Further developments in axiomatic set theory. Following Zermelo's work, other mathematicians sought to refine and extend axiomatic set theory. Freenkel and Skolem independently proposed modifications to Zermelo's original system, leading to the development of Zermelo-Freenkel set theory ZF, which is now a standard foundation for mathematics. The addition of the axiom of foundation to ZF, which prohibits sets from containing themselves either directly or indirectly, helped to eliminate certain paradoxes and to provide a more stable foundation for set theory. Further axioms, such as the axiom of large cardinals, have been proposed to address questions about the existence of very large infinite sets. The ZF set of axioms became dominant. Section 20. The ongoing debate about the foundations of mathematics. Despite the widespread acceptance of ZF set theory and the axiom of choice, debates about the foundations of mathematics continue to this day. Alternative foundational systems, such as category theory and univalent foundations, offer different perspectives on the nature of mathematical objects and the principles of mathematical reasoning. These alternative systems challenge the dominance of set theory and provide new tools for exploring the foundations of mathematics. Further research into these alternative foundations may lead to new insights into the nature of mathematical truth and the limits of mathematical knowledge. The claim is that, despite relative stability, mathematical foundations remain an active area of research. Section 21. Modern interpretations of Zermelo's proof. Contemporary mathematicians view Zermelo's proof through the lens of modern axiomatic set theory, recognizing the axiom of choice as a powerful and indispensable tool, while criticisms of the original proof remain relevant from a historical perspective. The modern understanding of the axiom of choice and its independence from other axioms has largely dispelled concerns about its validity. Zermelo's proof is now seen as a landmark achievement in the development of set theory, demonstrating the power of axiomatic reasoning and the importance of carefully considering the foundations of mathematics. The claims presented are now evaluated in light of the modern axiomatic background. Section 22. Enduring significance of Zermelo's contribution. Ernst Zermelo's 1904 paper, Prove that every set can be well ordered, represents a watershed moment in the history of mathematics. It introduced the axiom of choice into the mainstream lexicon, revealing both its power and its potential for controversy. While the initial proof faced criticism and underwent revisions, its enduring impact on set theory and mathematics as a whole is undeniable. Zermelo's daring assertion of the axiom of choice, coupled with his ingenious construction of gamma sets, forever altered the landscape of mathematical thought, paving the way for new discoveries and deeper insights into the nature of infinity. Even now, Zermelo's argument continues to serve as a testament to the courage required to challenge existing assumptions and to push the boundaries of mathematical knowledge. The final claim is that this paper fundamentally changed the intellectual landscape. In conclusion, Zermelo's proof, while sparking debate and requiring revisions, stands as a cornerstone of modern set theory. Its enduring significance lies not only in its conclusion, but also in forcing mathematicians to confront the implications of their foundational assumptions and to grapple with the mysteries of infinity. The work served as a catalyst for further exploration of axiomatic systems, forever shaping our understanding of the foundations of mathematics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.